So we want to close our discussion, our introduction to matrices real quick with a couple of important things and uses of matrices. One thing is I want to talk about partitioning of matrices. There's lots of ways this can be done. The way we're mainly going to see it is in terms of breaking up essentially the matrix into its columns and rows, or column vectors and row vectors. So if, right, the columns are the ones going down a matrix. If we let those columns just be column vectors, right, they're one column with, the same number of rows, the number of rows that are in the matrix. If we call those columns then C1, C2 all the way to Cn, because the matrix we're looking at A is M by N, so notice it has N columns. All right, then we can write the matrix A a little more compactly this way. Okay, and we're, of course, these column vectors individually would consist, this would be the first column of A, this would be the second column of A, and so on down to the nth column of A. And notice our double subscript notation in here, so this is A11 is row 1, column 1, row 2, column 1 entry, and so on, all the way down to row M, column 1 entry. Okay? And so these are the columns, partition, if you will, a way of breaking down and writing it a little more compactly. We can similarly do it with rows. So in the M by N matrix A, there's M rows. So if we look at those row vectors, which are one row, but in this case N columns long, right? Then we can write the matrix A this way, and where R1 is row 1 of the matrix and R2 is row 2, and so on. So this is a convenient way to break up a matrix. There are other ways as well that are very useful and helpful in different circumstances. Another thing that we will talk about quite a bit is to think about when we multiply a matrix on the left times a column vector on the right. Something interesting, a relationship happens. This statement says it, and then I'm going to illustrate it with this example. So if A is in general an M by N matrix and X is an N by 1 column vector, right? Notice I can multiply A times X because the inner number here, remember to do the multiplication, this inner number here has to match up, right? The number of columns of the matrix on the left must match the number of rows of the matrix on the right. So N and N. So we can talk about this product AX, and in that case that product can actually be expressed as a linear combination of the columns of A with the coefficients being the entries of the vector X. So we talked about linear combinations earlier, and so let's take a look at how this is true in this example. So I'm not going to prove this per se, but I'm going to look at this. Let's let this be the matrix A. In this case, this matrix is size 2 by 3, 2 rows and 3 columns, and let this be our vector X, right, which is 3 by 1. Notice I can again do the multiplication because this middle number matches. So this is a specific example of what we have here. Okay, so how would we do this multiplication? So we've talked about it. The resulting size is what the outer numbers tell us, 2 by 1, 2 rows, 1 column. Okay, 2 rows, 1 column. What's the first row going to be? Well, I'm going to take the first row in this matrix and multiply it by this column, or the dot product. Remember how that works. That's what, 3 times 7 plus negative 2 times negative 8 plus 6 times 2. And that's our first row in our 2 by 1 matrix. And then the second row is what? Take the second row times the column. Second row dotted with the column. So negative 1 times 7, and so on, for negative 8, negative 5, and 2. Okay, and so we can certainly do the arithmetic now and get these two quantities, right? We'll get our 2 by 1 matrix. But I want to, I'm trying to illustrate this. How how does this become a linear combination of the columns of A, in which the coefficients are the entries of X? What are the columns of A? You see we have 3 columns in the matrix A. So when you look at this, notice something. You can see the common multipliers of 7, -8, and 2 from our column vector X. And I'm going to simply rewrite this a little bit differently and see if you agree this is the same thing. 7, right, which is the same multiplier, times the vector, column vector 3, -1. And then plus, here the multiplier is -8 times the column vector -2, 4. And then here 2 times the column vector 6, -5. Okay? In both cases we're going to get the same result. Right? We're going to get the same result because this, though, is a linear combination, right, of 3 vectors, 3 2x1 matrices or 2x1 column vectors, right? So 7 times this one, how would I do that? Just scalar multiply, right? 7 times 3, 7 times -1, -8 times -2, 2 times 6, 2 times -5, and then we would add, right, the corresponding top component, corresponding bottom row component, and we get a result. That's exactly what we're doing here, though. Right? So both of these are going to result in a 2x1 vector, 2x1 matrix, right, which is the result here. But this indeed, you see, is what? A linear combination of what? What are these? These are indeed the columns of A. The first column is 3, -1, second column is -2, 4, and the third column is 6, -5. Right? So this is a linear combination, so abbreviate here, of the columns of A with coefficients from the vector X. Okay, so there's sort of 2 ways to think about matrix multiplication in this case, right? When I have a matrix times a column vector. And we'll return to this again and talk about that some more, but that's the first sort of illustration of that. The last thing is real useful. We've looked at the augmented matrix to represent a system of linear equations. So far in talking about matrices, we really haven't talked about systems of linear equations. We've just talked about matrices as objects in and of themselves. But now I want to talk again about another way to represent a system of linear equations. And here I have a general system of m linear equations and n unknowns. And so remember how this works. Our first equation here, second, third, the A11, A12, A13, and so on, those are the coefficients of the variables x1, x2, x3. Notice there's n variables, n unknowns, and the A12 is the coefficient of x sub 2 in the first equation. A13 is the coefficient of x sub 3 in the first equation. A23 is the coefficient of x sub 3 in the second equation. A31 is the coefficient of x sub 1 in the third equation. AMN is the coefficient of x sub n in the m equation, the mth equation, right, the last equation. So here it is, and I can represent this now as the following matrix equation. Matrix A, I'm simply going to put in the coefficients, right, corresponding to each of our variables in this matrix. Now it's m by n, right, because there are m rows, 1 for each equation, and n columns, 1 for each variable. And then I'm going to multiply this m by n matrix A by this vector x, which is simply our unknowns, right, in order x1 through xn. That's an n by 1. Notice I can do this multiplication because the n's match up, right? The n's match up. And what's the resulting size? M by 1. And that m by 1, these are the constants, right here. So notice when I do the multiplication, right, I get an m by n times n by 1 gives me this m by 1 equation. So what's this first entry here? It's going to be this first row dotted with this column. What's that? A11 times x1 plus A12 times x2 plus A13 times x3 and so on times A1n times xn, right? That is exactly what we have here. This is the dot product of that first row and that column, right? Equals what? B1. And then the second row dotted with this column gives me the second equation. Third row dotted with this column gives me, right, the third equation, and so on. So this is a compact way that I can now write this entire system as just AX equals B. And that's a much easier way than writing out, especially if you have 10 equations and 20 unknowns, right? We just represent it this way if we have to talk about it. Very compact. So very helpful. This will now represent a system of linear equations. And notice the size of this matrix A, which is what we call the coefficients matrix. Matrix A is the coefficient matrix, right? These are the coefficients. And the size of that coefficient matrix will depend on what? The number of equations and number of unknowns. The rows is the number of equations. The number of unknowns is the columns. That's every time for the coefficient matrix. Matrix B is sometimes called the constants matrix or vector, right? It's just our constants. And sometimes we talk about this vector X as being sort of like the solutions, right? These are the solutions to the system, the values of X that satisfy all the equations above. Okay. Now we talked about the augmented matrix. If I take this matrix A, the coefficient matrix, and attach, if you will, the constant matrix to it, or what we call adjoining it, so it's sort of a partition really, take A and then adjoin or partition on the B vector here, then I'm going to get a bigger matrix, right, which is of course our augmented matrix. That's all it is, right? Just take the coefficients and then the constants is the last column. Okay, so there's the connection. So let's just see this in closing real quick. Write the following system of linear equations in matrix forms as a matrix equation. And so I can write this as AX equals B. There it is. Where, of course, what are these AX and B? Where A is the coefficient matrix. And the coefficient matrix I'm just going to pull off. Notice I've got all the x1s, x2s, x3s lined up. So 3x1, coefficient of x1 in the first equation. Negative 2 is the coefficient of x of 2 in the first equation. And x3 has a coefficient of 1. Right? That's my first row from my coefficients matrix. Then what? 1. What do I put here? There's no x2, 0. And then negative 6. 1, 0, negative 6, 4, 1, 8. So there's my coefficient matrix. The vector B is my constants, right? That's a 3 by 1, right, where I'm just going to put in these constants, 7, negative 2, and 0. And of course, X is my variables or unknowns, right? And I'm just going to put X of 1, X of 2, X of 3. There. Okay. So there is that system written in matrix form, and very, very useful thing. We will use this quite a lot. Okay, so that's done with matrices introduction. We're going to look more in depth at the properties of matrices and their arithmetic in the next set of lecture videos.